It is the silent conductor of the cosmic ballet, the unseen architect of galaxies, and the first and last law we experience in our lives. It is gravity. We feel it in our bones, in the effort of a single step, in the simple act of a falling leaf. For millennia, humanity has lived under its unwavering rule, yet to truly understand it is to embark on a journey that rewrites the very nature of space-time and reality itself. This is the story of how we unraveled the universe's oldest law. For most of human history, gravity was not a mystery to be solved, but a simple fact of nature. The ancient Greeks, masters of logic and observation, were the first to formalize an explanation. For Aristotle, the universe was a place of order and purpose. Objects had a natural place. A rock, being made of earth, sought to return to the earth. Smoke, being airy, sought to rise to the sky. Heavy things fall, light things rise. It was an intuitive, earth-centric view. The heavens above were a different realm entirely, perfect and unchanging, where celestial bodies made of a divine substance called ether moved in perfect circles, forever bound to crystalline spheres. The laws of the messy terrestrial world did not apply to the perfect celestial one. This fundamental division between earth and the heavens would dominate Western thought for nearly 2,000 years. The first cracks in this ancient edifice appeared not with a new theory of gravity, but with a new map of the cosmos. In the 16th century, Nicolaus Copernicus, a Polish astronomer and cleric, proposed a radical, almost heretical idea that the Earth was not the center of the universe. Instead, he placed the Sun at the center, with the Earth and other planets revolving around it. While this model simplified many astronomical calculations, it was still bound by the old Greek ideal of perfect circles. The data didn't quite fit. The universe, it seemed, was more complex. The man who would truly break the celestial spheres was Johannes Kepler, a brilliant German mathematician and mystic. Kepler was obsessed with finding the divine geometry in the heavens. Working tirelessly with the meticulous astronomical data of his predecessor Tycho Brahe, Kepler tried for years to fit the orbit of Mars into a perfect circle. It refused to comply. In a moment of frustrated genius, he abandoned the circle and tried a different shape, the ellipse. Suddenly, everything clicked into place. Kepler formulated his 3 laws of planetary motion. Planets move in elliptical orbits with the Sun at one focus. They sweep out equal areas in equal times, meaning they move faster when closer to the Sun, and the square of their orbital period is proportional to the cube of their distance from the Sun. Kepler had described the how of the cosmos with breathtaking precision, but he did not know the why. What was this invisible hand guiding the planets on their elliptical paths, speeding them up and slowing them down? The mystery deepened. The answer would come from a mind forged in the crucible of plague and revolution. In 1665, as the Great Plague ravaged London, a young student from Cambridge University named Isaac Newton retreated to his family farm in Woolsthorpe. It was here, in a period of intense, solitary contemplation, that the seeds of our modern understanding of gravity were sown. The story of the falling apple, while likely an embellishment, captures the essence of his revolutionary insight. Newton watched the apple fall to the ground. He looked up at the moon hanging in the sky. Previous thinkers saw 2 separate phenomena governed by 2 separate sets of rules. Newton asked a question of staggering audacity. Could it be that the same mundane pull that brings an apple to the ground is the very same force that holds the moon in its orbit around the Earth, preventing it from flying off into space? This was the grand unification. The wall between the terrestrial and the celestial was torn down. The laws of physics were universal. Newton spent the next 2 decades developing the mathematical tools, including calculus, to describe this universal force. In his monumental work, the Principia Mathematica, published in 1687, he laid it all out. His law of universal gravitation stated that every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of their masses. and inversely proportional to the square of the distance between their centers. It was simple, elegant, and immensely powerful. With this single equation, one could explain the falling apple, the orbit of the moon, the elliptical paths of Kepler's planets, and the ebb and flow of the tides. Newton's gravity was a force that acted instantaneously across the vast emptiness of space, a cosmic string connecting all objects. The universe, in this view, was a giant, predictable clockwork machine set in motion by a divine watchmaker, running according to immutable laws that could be understood by human reason. For over 200 years, Newton's theory reigned supreme. It was so successful that when astronomers in the 19th century noticed Uranus was deviating slightly from its predicted orbit, they didn't question the law. Instead, they used Newton's equation to predict the existence and location of a new, unseen planet tugging on it. That is how Neptune was discovered in 1846, a stunning triumph for Newtonian physics. But even the most perfect clock can have a flaw, a tiny, persistent anomaly that refuses to be ignored. For Newton's gravity, that anomaly was the planet Mercury. The innermost planet's elliptical orbit slowly rotates or precesses. Over time, Newton's law predicted this precession, but it got the number wrong. The discrepancy was minuscule, a mere 43 arcseconds per century, an amount so small it's like watching the tip of a clock's hour hand move the width of a human hair. Yet, it was real. Astronomers tried everything to explain it. They searched for a hidden planet inside Mercury's orbit, which they named Vulcan. They never found it. They proposed that the sun was slightly squashed, or that a cloud of dust surrounded it. Nothing worked. For decades, the rogue orbit of Mercury was a quiet, unsettling whisper, a crack in the foundation of the perfect Newtonian universe. The man who would shatter that foundation was not an astronomer, but a patent clerk in Bern, Switzerland. In 1905, Albert Einstein published his theory of special relativity, which revealed a deep connection between space and time and established a new cosmic speed limit, the speed of light. This created a profound conflict with Newton's theory. If gravity was a force that acted instantaneously across space, as Newton proposed, then it violated Einstein's new principle. If the sun were to suddenly vanish, Newton's equations implied the Earth would instantly fly out of its orbit. But special relativity dictated that no information, not even the information of a gravitational change, could travel faster than light. It would take 8 minutes for the darkness to reach us, and therefore it must take at least 8 minutes for the gravitational effect to reach us. Gravity needed a new explanation. Einstein obsessed over this problem for a decade. The breakthrough came in 1907 with what he called the happiest thought of my life. He imagined a man falling from a roof. In the brief moments of free fall, before air resistance becomes significant, that man would feel weightless. If he were to drop objects from his pockets, they would float alongside him. From his perspective, gravity would have vanished. Einstein realized that the experience of being in a gravitational field is perfectly equivalent to the experience of being in an accelerated frame of reference. This was the equivalence principle. Imagine being in a rocket ship in deep space, far from any gravitational pull. If the rocket accelerates upwards, you will be pressed to the floor. If you drop a ball, it will fall to the floor, just as it would on Earth. You would have no way of knowing whether you were at rest on a massive planet or accelerating through empty space. This profound insight led Einstein to a revolutionary conclusion. What if gravity wasn't a force at all? What if it was a consequence of the geometry of the universe itself? He proposed that space and time are not a passive, static backdrop for the events of the universe, but a dynamic, interwoven fabric, space-time, and this fabric is not flat. It is curved and warped by the presence of mass and energy. The famous analogy is a bowling ball placed on a stretched rubber sheet. The ball creates a deep depression in the sheet. A marble rolled nearby will not travel in a straight line. It will follow the curve created by the bowling ball, perhaps even circling it in an orbit. The marble isn't being pulled by a mysterious force from the bowling ball. It is simply following the straightest possible path through a curved surface. This was the essence of Einstein's general theory of relativity, completed in 1915. In his elegant field equations, he described this relationship precisely. Mass tells spacetime how to curve, and curved spacetime tells matter how to move. Gravity is geometry. This new picture of the universe was bizarre and beautiful. It meant that time itself is affected by gravity. A clock at sea level ticks ever so slightly slower than a clock on a mountaintop, because gravity is stronger at sea level, warping spacetime more intensely. And what of Mercury's rogue orbit? Einstein applied his equations to the problem. The Sun, being immensely massive, creates a significant warp in the fabric of spacetime. Mercury, being the closest planet, travels through the most steeply curved part of this warp. As it orbits, it is not simply tracing a static ellipse, but an ellipse on a spacetime fabric that is itself being dragged and warped. When Einstein calculated the effect, it predicted the precession of Mercury's orbit perfectly, matching the observed 43 arcseconds per century exactly. The anomaly was explained. But a theory, no matter how beautiful, requires proof. Einstein's theory made another astonishing prediction. If massive objects curve spacetime, then light itself, though massless, should follow these curves. A beam of starlight passing near the Sun should be bent by the Sun's gravity. The effect would be tiny and impossible to observe under normal conditions, as the Sun's glare would overwhelm the starlight. But it could be tested during a total solar eclipse. In 1919, the British astronomer Sir Arthur Eddington led 2 expeditions, one to Brazil and one to the island of Principe off the coast of Africa, to photograph the stars around the Sun during a solar eclipse. It was a monumental undertaking. After months of travel and preparation, they waited for the few precious minutes of totality. The photographs were taken. When the plates were developed and compared to photographs of the same star field taken months earlier, the results were clear. The positions of the stars had shifted. The light had bent, and it had bent by the precise amount Einstein's theory had predicted. The news flashed around the world. The headlines were sensational. Newton's universe was overthrown. A new universe, a strange, curved, dynamic universe, had been revealed. Albert Einstein became a global icon overnight. In the century since, general relativity has passed every test thrown at it. Its effects are not just theoretical, they are woven into our modern technology. The GPS satellites in orbit around the Earth experience weaker gravity and are moving at high speeds. Their internal clocks tick faster than clocks on the ground. If engineers did not constantly correct for these relativistic effects, your GPS navigation would accumulate errors of several kilometers every single day. Einstein's theory also predicted even more exotic phenomena. It predicted that if a star massive enough were to collapse under its own gravity, it could curve spacetime so intensely that nothing, not even light, could escape. It would create a hole in the fabric of reality, a black hole. For decades, these were considered mere mathematical curiosities. But today we have observed them, even photographed the shadow of one at the heart of the M87 galaxy. Einstein's theory also predicted that cataclysmic events, like the collision of 2 black holes, would send out ripples in the fabric of spacetime itself. Like the ripples from a stone thrown into a pond, these are gravitational waves. For a century, they remained undetected. But in 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, a pair of instruments of almost unimaginable sensitivity, detected the faint chirp of a gravitational wave that had traveled for over 1 billion years to reach Earth, the echo of 2 black holes merging into one. We could now not only see the universe, but hear the rhythm of spacetime itself. And yet, the story is not over. The journey to understand gravity has led us to the edge of another great mystery. General relativity is a theory of the very large, of planets, stars, and galaxies. But the universe also has a theory of the very small, quantum mechanics, which governs the bizarre world of subatomic particles. These two pillars of modern physics are spectacularly successful in their own domains, but they are fundamentally incompatible. They speak different languages. General relativity describes a smooth, geometric universe, while quantum mechanics describes a fuzzy, probabilistic one. At the center of a black hole, or at the moment of the Big Bang, where the immense gravity of the large meets the tiny scale of the small, both theories break down. Gravity is the only one of the four fundamental forces of nature that has resisted inclusion into the quantum framework. The quest today is for a theory of quantum gravity, a theory of everything that can unite these two descriptions of reality. Physicists are exploring radical ideas like string theory, which posits that all particles are tiny vibrating strings, and loop quantum gravity, which suggests that space-time itself is made of discrete, indivisible chunks. We do not yet know the answer. The journey that began with Aristotle watching a rock fall, that was revolutionized by Newton watching an apple fall, and was transformed by Einstein imagining a man fall, continues. We have peeled back layer after layer of reality, from a force that pulls to a geometry that curves, and now, perhaps, to something even more fundamental. To fully understand gravity is to seek the ultimate source code of the cosmos, to read the mind of the universe itself, and that is a journey that has only just begun.